In this video, we're now going to discuss how we can use calculus to find area under a curve. So the two big ideas in calculus, first we learned limits because limits are used in both of these big ideas. So we looked at tangent lines and we applied limit to slope so that we could find exact rates of change rather than average rates of change. Now we're going to apply limits to rectangles so that we can find areas under curves. So just remember, this is sigma notation. It just means we're going to add together lots of similar terms, and we're going to use that in our definition of how to find area. So you're going to see this word Riemann sum. It's the process of using inscribed or circumscribed rectangles to estimate area under a curve. Again, this is an estimate, and then in the next couple chapters, we're going to make it more accurate by applying a limit. And then we're going to use function values, which are y values, to find heights of our rectangles. And so what we're doing here is we're taking a curve. So if I said, find the area under this curve, well, we don't have a geometric formula for that shape. So what we can do is we can use a process of a Riemann sum. And that just says, let's fit rectangles under here and use that to estimate. And we did that back in geometry. And we had like weird shapes, maybe on like coordinate grids, and then we had to count all the boxes to estimate kind of what the area was. And that's kind of what we're doing here, except we're being a little bit more systematic by using rectangles specifically. So this guy here, what we're going to do is we're going to have an interval. So here we're starting at 0, and we're going all the way to 2, and we're splitting this up into 5 pieces. Okay, so we have one interval here, an interval here, and because we split it up into 5 pieces, each interval is 2/5 of a unit wide. To find then our heights, we need to follow our direction. So they're either going to ask us to find a left hand, a right hand, or a midpoint Riemann sum. And so that just tells you what you're going to use to find your height. So if we're looking here at this very first interval, if I were to use a left-hand Riemann sum, that means in this interval, I'm going to plug in my left-hand endpoint to my function. So I'm going to come up here, I'm going to find this y value, and that will determine the height of the rectangle that we're going to use. So for this guy, we have a height of 5, and then we have a width here of 2/5. So to find the area, we're going to take 2/5 times 5, and that would give me the area of this first rectangle. Okay, obviously you can see with this process, we are going to have some extra area that we really don't need. So again, this is just an estimate. If we continue this process, by the time we get out to, let's say, this interval, again, this is a left-hand Riemann sum. So we're going to take 6/5. We're going to plug it into our function to determine the height of this rectangle that we'll calculate here. And then when we're done, we just add them all together. If they gave us the same scenario but said use a right-hand Riemann sum, now for this first interval, instead of plugging in 0, we're going to plug in 2/5 because it's the endpoint that's on the right. So its y value determines the height of this rectangle that we're going to calculate. If it's at a midpoint, then we would plug in the midpoint to determine the height. Okay, so when we look at area of a region, one way to calculate area, again, is to do length times width. So this y value gives me the height, and the difference in the x value gives me the width. So this is just length times width. This says we want to add them all together. Now, obviously, you can see from this last picture, when we use a right-hand Riemann sum, we have a lot of space that's kind of unaccounted for. So you can see it's an estimate. If we made more rectangles, the area would become more accurate. So this idea of applying a limit now says, what if we could fit an infinite amount of rectangles under our curve? And then we'll end up getting the exact area. Okay, so for this video, we're just going to practice finding Riemann sums, which are estimates. So you can read kind of through the steps if you want. The key thing is that we're finding the area of each rectangle, and we're just going to add them together. A trapezoidal sum is the same idea, except now we're going to fit trapezoids in under the curve instead of rectangles. So that's actually going to produce a more accurate area because instead of having all of that wasted space for a rectangle, now we're going to have a trapezoid. So you can see it's a little bit more accurate. And then don't panic about area of a trapezoid. A trapezoid it's kind of just like a fancy rectangle. The area of a rectangle is length times width. In this case, we actually have two lengths. So you can see here, each trapezoid has two lengths, so we need to just average them together. So this piece is just replaced by the average of, we call them the two bases, but they're just the two lengths. And then the width here is usually called the height. So that's the formula for the area of a trapezoid. And now we're going to do some examples. So in this case, it asks me to use a left-hand Riemann sum to evaluate this integral. And this integral, we'll learn it actually in the next video. This just says find the area under the curve. And so that's kind of what we're estimating here. So I like to kind of draw myself some rectangles. I usually don't go to the trouble of drawing an actual graph, but I just kind of say, okay, I know I'm going to be using 4 rectangles here. I don't know how tall they are. I don't really know what they're going to look like, but I'm going to calculate the area of each one and add them together. So because it says use a left-hand Riemann sum, that means I'm going to use my left-hand endpoint. So out of 2 and 3, 2 is on the left. So I use that to determine the height. So this guy has a height of 6. And then the difference between 2 and 3 is 1. So it has a width of 1. So the area of this first rectangle is 1 times 6, or 6. Okay? On the next one, we'll call this guy the blue one. He has a width of 2. And again, I'm going to use the left-hand endpoint to determine the height. And I know it doesn't really make sense for a rectangle to have a height of a -2, but we're using those y values. So it's going to really be -2 times +2. Now we'll call this guy the green one. The green one is going to have a width of 3. And then his height, again, is determined by that left-hand endpoint. So his height is -1. And again, guys, that just means he's outside, below the x-axis. And then finally, we'll look at our last rectangle. Here we have a width of 5. And then we're going to use this left-hand endpoint to determine that the height is 3. So 3 times 5 will give me the area of that rectangle. We would simplify this, and I believe that we get 14. Oops, I already got it up there. Okay, example 2 here. Again, this one now says find the midpoint sum. So now I'm using midpoints to calculate height. It does say that we're starting at 0 and we're ending at 2. So I do like to give myself that little visual. So 0 to 2. And it says we're using 4 subintervals of equal length. So I need to take these 2 units and split them up equally into 4 pieces. So that means each piece is a 1/2 of a unit wide. So I have this picture. And then again, just like I did in the last problem with my rectangles, I'm just going to draw some rectangles just so that I remember all I'm doing is calculating area of each one of these. So for this first one, its width is 1/2. Obviously, each of these has a width of 1/2. So that part's pretty easy. And the last problem, they had differing widths. So be careful, pay attention to your widths here. And then this one asked me to do a midpoint sum. So I'm actually going to plug in the midpoint here, which is 1/4, into my function to find the y value. In the last problem, these y values were given to us. Here, we have to actually calculate them. So for this first red rectangle, it has a width of 1/2. And then I just have to take that midpoint and plug it into my function to determine the width. The height. Okay? So for the next one, we'll call this guy the blue one. It also has a width of 1/2, but this time I'm going to plug in 3/4 because again, it wants me to use the midpoint of each interval to calculate the height. So I'm going to plug 3/4 into my function to determine the height. Next, we'll call this the green rectangle. So we have a width of 1/2, and its height is going to be calculated by plugging in, this is going to be 5/4. And again, I'm just plugging these in to this function, x squared. And then the last one, we'll go the black rectangle. We have a width of 1/2, and we're going to plug in here. It's going to be 7/4. And if you simplify, that will estimate the area under this curve. Okay. The last one we're going to do is a trapezoidal sum. Again, we're calculating area of this trapezoid. So I need to average the heights together. So I have two heights. I need to average them together. And then I need to multiply by the width. So this is kind of like length times width. Okay? For this next trapezoid, again, I just draw some random trapezoids here. I need to average these two heights. So 0.8 plus 0.7. And then I'm multiplying by the width. Okay? I'm going to continue this process. Now I'm averaging together the two heights of the next trapezoid. And I'm multiplying by the width, which is 3. And then finally, I'm going to average the two. So I have 1/2 of 0.4 plus 0.2 times the width of this interval, which is 2. And if I simplify, I get an estimate for the area under this curve.